Hello everyone, this is Mohammad Abdulaziz, and today I will be doing the 7th tutorial of the Function Data Structures course. So in this exercise, in this tutorial we have two exercises, so I'll start with the first one quickly. So suppose you have a binary search tree that has integer elements stored in its nodes, and in this exercise we want to devise a function that, given an integer, returns to you the closest integer that is stored in the tree to the given integer. Okay? So, for example, if you have a tree like that, and you're given, for example, 0, then you want to return 1. If you're given 1, then you want to return 1. If you're given 2, then you return 2, etc. So we want also, because this is a binary search tree, we want to design this function such that it doesn't do unnecessary recursion. So, for instance, if we're given 1 in this case, we don't want to search for the one on the right and then on the left. No, we want to only descend to one of the two subtrees depending on the value that we're searching for. So I suggest you pause the video and try and implement this function by yourself. But I will do it right now. So that is the function. Yeah, and I forgot actually to say something, that the function should return an option, as in if the element that you're looking, if the tree is empty, it just returns nothing. So it should return none. Otherwise, it should return the closest element. So that's it. So it should be recursive. Yep, so if it's a leaf, then you should return none. If it has data stored in it, so in this case, you will do the following. So you if A is equal to B, then just return A, sum A. Otherwise, if A is smaller, then you only go to the left. Sorry. B is smaller than A, and go to the left. Else you go to the right. But of course you shouldn't do that, because because a problem with this function I will show you right now on the paper. So for instance, like if you're searching for a 1, for a 2 in this, no, let me just, it's a different example then. So let's say you're given a tree like that, 1, 2, 3, sorry, 1, 2, 5, okay, and then here, okay, and then if we're searching for 4 here, with the count function, you would go to the left, because 4 is smaller than 5, and then, for example, if this is just a if this doesn't have the right subtree, then you will return none. Okay, but we wanted to return the closest member to 4, which is 5. In this case, you go to the left, and then because it's not smaller and not equal, so you just go to the right, which is a leaf, and then you return none. So what we want to do is to basically compare when you go down to the left, for instance, you should compare how close the value that you got by calling a function on that subtree is to the value stored in the current to the value. You want to compare the value returned from the left subtree to the value that you're searching for, and compare the difference between those two values to the difference between that and the current element, so 4 and 5. So in this case, 5 will be closer, and that's why we should return 5. So we want to implement that comparison. So I'll just write a function. Let me say closer, where so this function should take 3 values. It should take the value you're searching for, and the value returned from one of the subtrees, and the value in the current node. So the value you're searching for equal B, the value returned from the value in the current node, which I will just call it A, and the value returned from the search, which I will just call it C. And then you would do the following. So if what you have from the next node is none, then you will just return A. Otherwise, if it is some value, then we should return whichever is closer. So if the absolute difference between B and A is smaller than or equal the absolute difference between B and B, then we should return A, otherwise return B. Okay. And then here we just return the closer between. Oh, actually, this should also be sum. So the closer between B, which is what we're searching for, and A and the left, what comes from the left subtree, and the same for the right subtree. So that's it, the function. So now the next question is to prove that this function basically does what it's supposed to do, and what that means is showing that it returns none only in the case that the tree is empty, and that it returns only elements of the tree, and that the return element has actually the minimum distance. Okay, so I suggest you pause this video and try and phrase these these theorems by yourself, and also prove them, but I will do that now. But I really strongly suggest you try and do that yourself, because this is not something that that we will test in the homework. Because in the homeworks we usually state the theorems for you because of the nature of the competition system. So I suggest you try and phrase these lemmas yourself to learn how to do that. Okay, so I'll now state the first one. So the first lemma is round for a certain tree and a certain value, it returns none if and only if the tree is empty. So because the function is recursive on the tree, we do this by induction on the tree. Yeah, we need to think. Yeah, unfold the definition of closer. The second lemma is that if round returns something, then that thing is in the tree. So again, I'll find it by induction in the tree. So we need to split the if then else and the option splits as well. Yeah, we're done. The third lemma is that the return element actually has the minimum distance, and the way we would state that is as follows. So if round PB equals some C and A is in the tree, then the difference between C and B is smaller than or equal to the distance between A and B. Is that how we write? Let's just do it the other way around so that we can match the definition of closure. Yeah, actually, so here we have a counterexample, and this would only actually work if the tree is a binary search tree, because otherwise you might have missed the closure element on the different subtree. So let's try and do this with induction as well on the tree. Okay, let's see. Okay, so I'll do the splitting. Let's see again the goal. Maybe we should do an ease-out proof actually here. So let's do the splitting. So if splits, and then we need option splits here. Okay, so now everything is flattened. So, okay, so here we have a contradiction because that is equal to none, and that is and there is an element A in the tree 1, and remember this lemma that we have there says that this cannot happen. So if round returns none, then it will always, it means that the tree is empty. So I will just add this lemma to the sim set, and then hopefully that sub goal will now be gone. Okay, and now let's see what the sub goal looks like. So that should shouldn't that this should follow from this or that. So let's see what the assumptions of this are. That x2a is C. So what is x2a? x2a is what we get when we go to the left subtree. Okay, so let's analyze that slowly. So here we're looking for the closest thing to B, and it turns out that it is C in the tree T. Okay, and then we're saying that C we want for, okay, so that C is what we got from looking into the left subtree. Okay, and okay, so that's what we want. I mean, we want C to be what we got from the left subtree, and we are saying here that C is strictly greater than B. So that's, we cannot actually use that assumption, because if C is greater than B, yeah, this cannot happen. Okay, if we only go to the left subtree if the current element, yeah, no, it can happen. Yeah, if the current element is greater than, if the current element is greater than B. So anyway, yeah, so we either need to show that this C comes from the left subtree. Can we show that? Okay, let's look at the other assumption. Maybe it's easier to show. Okay, so basically here, what I'm doing is I'm looking for these for facts in the assumptions whose conclusion matches what we want to prove, and then I'm trying to prove their assumptions. So I'm saying we either need to prove that x2a is C, or that the right subtree returns C, and A is in the right subtree. Yeah, so this definitely, so we definitely cannot use that here, at least as it is. And B minus A is like that. So yeah, I'm just wondering, we probably need to generalize the induction hypothesis here. So you know what, I'll just try the hammer and see if there is some, because sometimes there is a contradiction in the assumptions that something like Metis or Fast Force can find, and you search for that with Sledgehammer. I'll try 0. Okay. Yeah, so we probably need to change induction hypothesis. C minus B minus A. So let's analyze that slowly. So the part of the induction hypothesis concerning the left subtree should say something that is like that, but it has been somehow simplified. But it should be saying basically that whatever round returns from the left subtree is closer to B than any other element of the left subtree. Okay, and then another element in the left subtree is A, and accordingly we would have our conclusion. But let's slowly understand that. So here, here we have a left subtree and A. Sorry. So what is the middle element called? So okay. So let's just So this is whatever the root is called, and this is the left subtree T1. Okay, and this is the right subtree. But we don't really care about it now. So the left subtree T1. The closest thing to be in here is x to A. All right. That's why it was returned by that function, by calling round on the T1. Yeah, and the induction hypothesis on the left hand side should say, from the left hand side should say that the distance between so if A is in the left subtree, then the distance between x to A and B is smaller than or equal to the distance between A and B. Okay? And what we want to say is that C minus B, the distance between B and C is smaller than or equal to the distance between B and A. So how would that look like there? If we have that x2a minus b is smaller, this difference is smaller than or equal to that one, and we have that even something. I will try and do the induction with the induction principle. One second. Rule around the induct. And this is clearer. Okay. So now we have the cases split clearly. And let me read that. So again, it's the same, but at least before we apply auto, things are clearer. So basically, the left, this is what concerns us. Like in this first sub goal, we're talking here about L, which is the left subtree, or T1 previously. So A is in L, okay? So let's go back to the induction hypothesis and slowly analyze it. So if you have so AA is the current root, and if what you're searching for is not the same as AA, and it is less than AA, and the left is a bit BST, then if the result the result of rounding on the left subtree is some C, something called C. And A is in the left subtree, then that. But what if? Okay, so let's go back there. So here, this C has been called x2 because it is actually different from the C that returns to us, right? That's the only reason it would be called a different name. So the result of rounding on the left subtree is some x2, and we know that we know that B and X, like the difference between B and x2 is greater than between C and B. Okay. But we need to somehow compare the difference between B and x2 and B and A. Okay, so let's go back to the induction hypothesis. So we need, yes, that's the problem. We need to generalize C here. Because we need the difference between B and x2 to be smaller than the difference between B and A. And then by transitivity, we would have from this and that other conclusion, we would have that. So let's look into this one more time. Okay, so if this would be just any general C, this would be that x2, and then we would have that difference between B and x2 is more than equal to the difference between B and A. So let us try and do that. Arbitrary C. Okay, so what the HOL is looking like now. So actually phosphorus will do it for us, and I suppose that the next one will be just the other direction. Okay, so now this is also another thing I would like to show you. So here, instead of having two separate calls, instead of calling O2 and then phosphorus like that, usually you can just do that. You can just call phosphorus and it will do the whole thing for you. Let's see. Yeah, it does it for us. So that is the proof of the second requirement. Now the proof. Now the next requirement is to estimate the runtime of that function. So let us be more precise. So here, what I want to estimate in particular is the number of recursive calls for this function. And if you want to estimate, so let's write the function that estimates the recursive calls. Note that this is different from the number of, previously we had additions, for instance, or like it's not always the case. When we say we just want to estimate the runtime, usually a good indication is just the number of recursive calls, but a lot of the times you just want to estimate the additions or the comparisons, for instance, when we're evaluating sort. Okay, so it should be that. Okay, and then T, and then the base case. So this is the last recursive call, and for that, here it should be one call, and this should be 1 plus that. Okay, so now what we need to prove about that is that it is linear. So let's firstly try and see the okay, so lemma, let me just try and do that. T round as T and any element is less than or equal to the height of T. Let's see, I don't know if we'll need a +1 or what, yeah. Let's see, okay, let's just try and see what is these runtimes value of T round what is the counterexample again? Empty, yeah, empty and -1. So this is 1 and the height of that is 0, so we probably need just a 1 there. So let's just make sure that there are no counterexamples, at least. Okay, that doesn't prove that there are no counterexamples, it just shows that Nipkow cannot find one in time. So let's do again the proof by induction on T. And apply photo. Okay, so it does it. And the proof is done. So now let's start with the second exercise. And it is about data structure called interval lists. So basically here we want to store, it's an efficient way, a space efficient way of storing sets of ordered elements. So for instance, if you want to store that set in this interval list, you can just store them as the ranges from 2 to 3 and from 5 to 5 and then from 7 to 9. This would be more efficient if the data is more dense. So for example, if you have 6 as well, then this would be just 2, 3 and 5 to 9. So then let's just take that type synonym. So that is the type. Okay. Now we want to define an invariant that basically says that the intervals are ordered and are disjoint. Okay, so the intervals are ordered and non-empty and disjoint. Yeah. So we will actually need, so to define that invariant on 2 stages. The first one is we will define a general one. So it takes a natural number as its argument. Okay. So let us see. So so invariant prime of anything. So here we do it recursively over the list. I mean, over the list of intervals. Yeah. So the empty list is is this invariant applied to the empty list, and then for the other case where we have an interval like that. So here IV, so then we would say, because this is a pair, so case IV of L and H, for instance, we would say here, so the first requirement is that L is less than or equal to H, okay? So that is the first requirement we have here, so let's just go to that part. So the first requirement is the this one. This is the second. We actually did the second requirement first. So we want that the ascending order and that the intervals should be disjoint will be the next requirement. And okay, so here. So this is a natural number. We would just say L is greater than that natural number, and L is smaller than or equal to H. And the rest of the list satisfies the invariant, but not just with n, but in fact n plus 2. So that's basically the next invariant starts at n plus 2, which is and this is to satisfy the fact that the intervals should be chosen as large as possible, because if they're chosen as large as possible, then the gap between each two of them should be 2. Otherwise, you could have merged the two intervals together. So invariant prime of that, and then are these. And then that actually shouldn't suck n, that should be suck h, I think, yeah, because you want the interval to start 2 numbers after the upper bound of the smaller interval, okay? So let's go to the next. So the actual invariant that we want. So inv equals inv prime of 0. Of invariants. So what is wrong here? So now the next thing is that okay, so basically we want to now write a function that, given an interval, gives you the set of elements stored in that interval. So the function should be set of set of again recursively, so it should be the empty set, and yeah, then another interval set of IVs What should that be? That should be the elements from L to H again. So here, case IV of LH. Then I want to get the set from L to H union set of IVs. Okay, that is exactly the right thing. Yeah. So yeah, now let us define a function that adds an element to the interval. So here I will actually maybe I should go to the paper first. So we need to consider many different cases when we're doing that function. So the first case is okay, so let me just try and do that on paper first. So let's say we have an interval like that. Okay, this is an interval list, and that's the first lower bound, first upper bound, second lower bound, second upper bound, etc. Now if we want to insert an element, well, the first case is the element is one smaller than that. Okay, let's say first. So case one is when if we want to insert an element A and that element is is smaller than or equal to L1 minus 2. Okay, so A smaller than or equal to L1 minus 2. Then the second case is if A is equal to L1 minus 1. So okay, so in this case you must create a new interval here for A. And in this case you must just make this interval bigger. Okay, and then case 3 when A is between L1 and H1. So okay, and then in this case nothing, we just return the same list. And then case 4, if A is 1 greater than H1, so A equals H1 plus 1. And then case 5 is when A is greater than or equal to H1 plus 2. And then in this case you will just either touch that interval or create a new interval, but one second. So let's say if A is greater than H1 plus 2, let's say that it is indeed equal to H1 plus 2. So this case we just remove that we recursively do the same function but with this interval removed. But the problem is with this case. If A equals H plus 1, then we will need to extend this interval with one element, with one extra element, A here, and then we want to make sure that that still this extended element doesn't need to be merged with the next one. So the extended interval doesn't need to be merged with the next one. So the invariant that we have already says that the next interval will start at h1 plus 2 at least. Yeah, so if it isn't, if so basically this is the most annoying case. So if you have L1 equal h1 plus 2, okay, L2 is equals to h1 plus 2, and then a equals h1 plus 1, then in this case you just want to return L1 to h2. Like in this case you want to return L1 to h2 and then remove both of those intervals. So in this case, in order for us to handle that case, we need to do the following. Let us now write the function and then do the different cases. Okay, so function add element, where so if we add, okay, so firstly this function will be recursive on the list of intervals, so add a empty list should just give us that interval, okay, and the next case a given IV cons IVs, then in this case LH. Okay, so in this case we'll have a few different cases that I just put in this paper. So if A is less than or equal, so if A is less than or equal to what? To L1 minus 2, to L minus 2 basically here in this case, then what? Then we should start a new interval for A. A, and then cons intervals. Let's just see if that type checks. Okay, so there's a problem here. Oh yeah, this should be the singleton list. Okay. So the first case is that. The second case is if it is equal to L. It is indeed equal to L minus 1. And then in this case we should so here we should return the two intervals actually, sorry about that. Okay, and this one we should return A and H, okay, and then the third case is when A is in the interval. So A here should be less than or equal to H. In this case, we should return L and H, the same intervals, so nothing should happen. And then the fourth case, which is the most annoying one, is when A is equal to H plus 1. And then last case. So this case, firstly, let's handle this case. So in this case, we basically will need to merge that first interval with the next interval, if there is a next interval, and if there is not a next interval, then we would like to just extend this interval with one element. Okay. So we're going. So here we can just do this here, or we define a separate function for it, but I'll just try and do it here and see if it's not too messy, then it's fine. So case IVs of IV prime, IVs prime, okay. In the case there is another interval, it's going to be too messy, I think. Let's just do it as a separate function. So I'll just call this merge intervals. Okay, so this function takes an interval and an empty list. Okay, and in the case it is an empty list, which means that here this IVs doesn't have other intervals, and in this case I will just extend So in this case, we will just return L in H plus 1. Okay. And in the other case, we have another interval. So this is IV prime and IV is prime. Then in this case, okay, I will just, we don't need that, we can just, I think we can just do matching, pattern matching on the pair. Okay. So here IV prime of L prime H prime. Then in this case we want to merge both intervals, so it will be L and H prime, and that should be it. And then we need to call that, so merge IVs of the current IV and IVs, right? Yeah, of course here we need IVs prime, and this one should just be a single canvas like that. Okay, so now it checks, and then the last case is when A is greater than or equal to H plus 1 plus 2. Then in this case we just insert in this case we just insert in the rest of the list of intervals. So here it's IV, add A IVs. Right. Okay. And now if we're going, so now we need to show that this function works well. So let me just try and see if it gives us the expected values. So I will just say add 1 to the empty list and see. Okay, let's see some concrete type. Okay, so 1 and 1, fine. So let us say here we have 2 and 3, 1 and 3. Let's say we have 3 and 3, give us 1, 2, 3. And let's say here that we have 0, 0. Okay, so 0, 3. Yeah, that is a mistake because here we add 2. So I think there's a mistake in the function itself out there. Because this way we added 2 inadvertently. So let us go back to the cases. So a is equals h plus 1. Yeah, well, it only would work if the invariant applies, and let me see. Yeah, the invariant applies to that list. Okay, so it probably is because of that case. I'll just try and return an empty set list or something in this case. Yeah, we're in this case. So let us debug that. So if a equals h plus 1, which is here, so a equals 0 plus 1, we would go to that function. Yeah, well, the merging, yeah, I forgot something important, which is to check if h prime is the same, yeah, okay. So here, if h prime is this equals h plus 2, okay, then we have that, we merge. Otherwise, we just extend the first interval and then append it to the whole list of intervals, okay? Okay, and now let's see what's going on down there. Okay, so that fixes the bug that we had. Okay, and now let us start doing the lemma. So lemma and correct. Assumes that in the invariant applied to some list of invariants, some list of intervals, and we want to show that the invariant holds in the new list. Okay, so that doesn't work. So we probably have a problem with the invariant definition of invariant. So let me just see if the invariant is true for that list. It is true. Okay, so let me just try and add 0 to that list and see. False, okay. So let us see what is the list that results from that. Yeah, we need this jointness, okay. Here we have the same list where we can have the same invariant added more than once. So here we should fall it should be that case that we are falling into. So I will just try and make this undefined and see what happens here. Okay, we're not in the right case. So which case are we in? Not that either. Not that. We're in the first case. So here A is okay. So the problem is that 0 minus 2 yeah, the problem is that 0 minus 2 is 0, so that's why we do that. So we need to reorder the cases. We need to have this first of all, we need to have this like that and reorder the cases. Okay, so let's see what happens now. No. Okay. Again, we have the same problem. So here we get into the wrong case because 1 minus 2 is 0. Because this is the problem of adding natural numbers, subtracting the natural numbers. Okay, so actually I also want to show you something small. If we want to not have that there, we can just say declare names short. Okay, let's see now. Yeah, we don't have that. Sometimes you have a theory name inadvertently. Okay, so now we can do this by induction. Apply induction xivs. I will do that. Let me try and apply auto and see what happens. See how many of the subgoals will go. We probably will need to have lemmas there. So he must. There's a contradiction probably. So this is not helping me. Having the computational induction like that isn't very helpful. It doesn't make a big difference. So if A is less than or equal to B, then so first we have a contradiction somewhere, and so if A is less than yeah, we need to have arbitrary x there. I hope. But even if we do the arbitrary x, will not work because this applies to 0. Okay, this invariant prime applies to 0 constant, and that's not. So we need to prove the lemma for invariant prime for any m. So let's try and do that. But yeah, but then what should the relationship between x and n be? That is the question. So let's go back to this invariant and see what it means. Yeah, we need to be, so this n should be smaller than or equal to the smallest lower bound in the interval list. And while here we have that n is greater than x, so we need the assumption that the other way around, that n is more at least smaller than or equal to x, and see what happens. Okay, so now so we have invariant prime of exact v wait a second, so here we have a is smaller than or equal to b and b is smaller than or equal to a minus 2. What that means is should be a contradiction actually, right? So if a is less than or equal to b and b plus 1 is less than or equal to a minus 2, that should be a contradiction. Let's see, that should be the contradiction that we want. I hope, at least. Okay. It should be doable by with something simple, I hope. Yeah, a simp. Okay, so that's the first sub goal. I mean, I'm going to do that to debug the proof and then clean up the proof really. The next thing is so here we're merging the interval. So okay, so it's not clear to me what's wrong. So let me just run think we need to state like that. I just getting these assumptions to be stated more neatly. Okay, so now again, let me just try and see if there is a counterexample for digging into the subgoal. Okay, so there is a counterexample. So if we have n0 and then x1 and then insert x, which is 1 there, let's see that. Let's try that counterexample. So here we have this, and then we're inserting 1. And then, yeah, we didn't merge. So here we should have merged, but we didn't. Let's go back to the definition again. So which case is that? So here we have the 1 to be greater than, so it's not here. And is it equal to that? No, it's not that. Is it equal? No, it's not that. It is equal to that. And then we're supposed to be merging, so let's just confirm that we are in this. Okay, and then here, yeah, that is the problem. So let's see what happens when you're merging there. So here you're having a lower bound and an upper bound of zeros, and we're saying if the new upper bound is equal to the old one plus 2, then merge. So shouldn't it be that? Otherwise we don't merge. So let me just try and merge. Yeah. So value merge IVs. See. Yeah, it didn't work. So we're supposed to, let me just try and make this undefined to make sure that we are in this case. Okay, we don't go to the right case. So here we do not go to the right case, and the reason for that is unclear. Just make sure that we go to the wrong case. Yeah, we go to the wrong case. Okay. Why is that? So here we have, so this is L and this is H, and this is L prime and this is H prime, and then we have here, yeah, well, H prime equals H plus 2. Strange. So here we have L prime equals A. H plus this should be L prime. Okay. See, this is a problem of this online teaching, that I don't have. Usually, the students would, like when you have 100 eyes over the same problem, the students would immediately tell you this is the problem or this isn't the problem. So anyway, let's see now how so that worked as expected. So I'm waiting now to see if there's another counterexample. I hope there isn't. Let's go to the proof again. So if we didn't find anything. So now we're back. So we need to know, so if invariant prime so let me just try and sledgehammer that and see. But in the meantime, trying to understand it. So so basically here we want to get this to get that form. Okay, so if we add let's show anything. So maybe we should go to the pen and paper then to understand the case. Okay, let me just see. So invariant holds for such that B on IDs. So that means n B is greater than or equal to n. So I think we're running into some complications there because we're using minuses. So here, this is one thing that we have to do. We should be using because as you have seen, when you have minus, like use whenever possible, try and avoid using minus with natural numbers, because you will get into cases where you will basically. So here, for instance, this was L minus 2 is greater than something, and then this gives us three possibilities for L. L could be empty, or it could be L could be 0, or could be 1, or could be 2, and all of them will give us the same result. So I think one complication we are having there is because we're using minus, and I think we shouldn't do that. Right. So whenever possible, you should avoid using -1. You're using natural numbers because you can, like for instance, this L there, we're having some condition on L -2, and that means that we need to do 3 cases. L could be 2 or 1 or 0, and all of them will, for all of those 3 cases, L -2 will be 0. So now that we have changed it to sub like that, let us see the sub goals. Yeah, so it's clearer, slightly at least. So let's see. So now we have invariant prime. So here we would. Okay, so here we have 2 cases. The first case is when we merge, so it means that we go there, and the second case, it's unclear to me. So either. So which one's the second? Okay, let's just get done with the first case and see. So here, let's call these, so A, B, I, V, so A is, so just go for L, H, and V's, okay? And then now we have that, okay, so we want to transform this into that form, and the only way for us to do that is by splitting on the data type of, splitting on the list of intervals, so that if it is empty, we will then get that this holds from the fact that L is greater than or equal to N, and if it is not empty, then this will be rewritten in a way that looks like that. Let us do that. IVs. Okay, that is the first sub-goal, and then the second sub-goal, yeah, now I don't really understand where did this come from. So basically this sub-goal is one of those cases. Must be a contradiction for it. So here we have an X and N, here we have an N, and this is suck B. Okay, so basically we want to say that yeah, we want to generalize this N here. So arbitrary N. Let me see this. Yeah, we're done. Okay, now that is this, and you can just make this look slightly better than that by starting a proof. So photo and then here yeah, okay, so that then from that we will know that this lemma should hold from the one above us, because x is a natural number, so it's always going to be greater than or equal to 0. We'll just call this auxiliary. So using that, by auto sim in definition. Yeah. Okay, so that's the first lemma. The second one, well, the second part of the lemma is that this thing works, the addition works as it's supposed to. So that should be, we have the invariant, then set of and x IVs equals insert x into set of IVs. So so let's look into the induction. So I would try and do it with induction on IPs, but it might be the case that we would actually, that it would be better to do it by induction on the add, using the add induction principle. So for this case, let's just hope that the base case goes by auto. Okay. Okay, then so we can just obtain that from the induction principle. From the induction hypothesis we can get that, and then let's just try and last the sub goes over on C, so here we need so let's see what that looks like. Yeah, so I just want to remember again what is set of. Okay. Yeah, so now I would consider having a separate lemma for each one of the cases of add. So proving that putting a separate lemma directly on this on this union for every separate case of the add, and seeing how that works. So firstly, can we go down there and see? clear. So here in this case we have the now I'll just do separate on the side. So here we can have so yeah, maybe well actually let me just remove that. Let's just work directly on that. Okay, so if we add something here, and if we have that this invariant prime holds to n, then we have that some for some m, then we have this k, we have this, we have the right conclusion, we have the right addition, we have the right set with the new insert element, and then I will try and do an induction on IDs. Okay, you could also try and do an induction. Let me just do that first and see. I'm gonna apply auto. So now we don't have down here. I think the fact that we needed to expand this was causing some complications. So let's use the induction principle that comes from that, so that we have a clearer. We have a clear induction hypothesis that. So here the induction hypothesis is unclear. We need to split this into pairs, and we don't know what the conditions are. So I'll just say rule induct rule in prime induct. And now so I will just try one thing, because I don't want this extreme expansion to happen. I will remove merge IVs simps, because I don't want that to be rewritten for now, and see how it looks like. Del that simps. Just don't have the same 8 subgoal, but at least we understand where we are. And then split. Splits. Okay, so these are just to split those if then else conditions. Okay. So now there might also be, I just would like, so this is basically we're trying, this is about a subset relation. Like this by experience you can say that, okay, so if x is in this thing, then x is greater than or equal to a. If in there, yeah. So we have it. So x is in this, then x is greater than or equal to a. So this a and b are the lower and upper. Those how about this? I just would like to rewrite this with a separate lemma. So lemma. So here I'm just going blindly. It could be the case that this is not useful, but I want to rewrite this into. So basically, I want to show that this is equal to A to B union set of B's. Okay, so let's just say, I just want to try if this lemma would help us. So yeah, it indeed did help us and remove many of the sub-goals. Of course this will not work as nicely, there must be some assumptions that at least so I'll just see if this sub-goal firstly is doable or no. Okay, it's not clear. So what is the sub-goal saying? That the subcluster B is in the set of IVs. So here we have that where is this x coming from? This is what we're adding, right? So here if you insert sub B into set of ideas, you have that. Yeah, that is equal to the adding sub B into ideas. And this only holds it for some x and y. Yeah, that are basically a and b. Yeah, this seems like it is something that doesn't hold. So let's think about this case on paper. So here we have so here we have x that we're inserting. So here we have the a and b. Okay, so a and b is the interval list, and then we want to insert x. And then x happens to be equal to b plus 1. Okay. So x equals b plus 1. Okay. And then what that takes us to, and then here we want to say that b plus 1 is in the set of elements of IVs. Okay. Why would that be? I'm just trying to understand which case. So if x is equal to b plus 1, which is the upper limit of the interval, then this means that we're in this case, and then we're merging here. And then wait a second. But if we're merging, then it should be Yeah, it shouldn't add then will return to us either that which either that or that. And here what we have here is that suck B is instead of IVs means that it only returned an interval and IVs, but that interval didn't contain suck B. So let us try and find a counterexample to that specific goal to understand what is that, if that makes sense. So sometimes these like when you use nitpick in the middle of a proof state like that, sometimes it gives spurious counterexamples, but some other times they are meaningful. So here we're saying that you got we're trying to insert 1, and then we have an interval a, b, and 0, and then the rest is empty. There are no other intervals. Does that make any sense? Let me go back there, and then equals 0. Okay, I'll go back one step and try and figure out where that came from. So we're trying to insert x. Yeah, so we're trying to insert x here, and then x is okay, suck B, and then we want to say that x so x is in yeah, I'm not able to understand why is this. How did we reach that position? So if I say x equals suck B, this means that I'm trying to insert into an interval that was shown in the paper there. But where? Why? Basically, the question is if we in this case that I set, in this case that's demonstrated on the video in the paper there, what should happen is you go there and then merge, and then this, instead of having set of IVs, you would be having set of merge IVs, IV, and IVs. Okay, and one of those two cases, but I don't really know which one are we into. You know something? Okay, as usual, I'll just trace it by calling something undefined and trying and see where that would fail. So here, so we're not in that case. Let's try in that case. Does that make sense? We're not in that case either. So where do we not add anything to the list? Maybe in that case I'll just try this. This is where we don't add anything. Yeah. So let's. Okay, so here we're trying to add something. and that thing is in between L and H. And here we're trying to insert an X, but that X is bigger than B, which I thought it should be in this case because X equals suck B. Let me just change that to suck as well, match the other ones. Okay, it broke some proofs. Yeah, because this one is probably also needs to be suck. Okay. Still, then we can just say X is greater than such H, and then hopefully this would guide the proof into the right cases. It doesn't. Before like that. Okay, it's messing something up. Yeah, that's why. Okay, so everything. And this should go here, suck, suck. And this should just suck. Okay, so doesn't make a difference, it seems like it. So what is let me just go up there again. So we're saying, as I'm showing in the video, that in the paper, that we are in the case where x equals b plus 1, so we're somewhere here. So let's just revise that. So if L prime equals such like h, we merge the two intervals because we already have that a equals such h. Otherwise, we extend the first interval, and that's it. Okay. So let me just make sure that I'll just try and get it. Make sure that we're in this branch by changing it. And this is a good heuristic. You can just insert undefined, and then it usually works like that. So it's not this. Maybe here. Well, that's unlikely because we have an IVs down there. still. Okay, let me just make sure that we're there. Yeah, this is our case. So somehow we go in here, but it's, let me just turn both into undefined and C. Okay, it's weird. So basically here we're having something that says that we go into that case but return okay. We go into that case, what return either this or that, and this suck B is not in those two intervals, or in not in that interval. Okay, so I'll just go back to the definition of merge. So here what we have is, yeah, it's definitely this case. This is the problematic case. Yeah, as you can see there. But actually it doesn't make a difference. Yeah, so it is this case. So the problem must certainly be in merge IVs. So okay, so let's just focus on merge. So if the value that we're adding is suck H. Okay. Okay, how about this? I just want to make it clear that we're passing that. Okay, so we already are passing that. So then in this case, only, okay, so this successor was added just once outside to eliminate any possibility of errors. Okay, so there must have been a bug in that. There must have been a bug in the way. Alright, just don't think this condition is needed either. Let's see. Yeah. So, oh yeah, okay, so let's just focus on this lemma first. So this lemma, of course, will not hold unconditionally like that. Let's see. So because this is not a recursive function, I will just do cases on IVs and see. Okay, so again we need to split the ifs. Okay, so let us try to conclude this. Okay, let us just try to conclude, to come up with the assumptions that this needs in order for it to work. So merge is the one that merges the two first intervals if need be. It merges. So firstly we need to make sure that So firstly, okay, so here we're taking this step. Here we're basically merging them into two intervals, and that is only valid if we have that if we have that the invariant of the interval list holds, but with a +1, as in the original invariant says that the distance between any two consecutive intervals is 2, but here when we call this function, when we go into this function, we already have increased the distance, the upper bound of one interval with 1. So we need to make sure that the invariant holds the invariant holds, let's see, in prime is this really okay? Okay, so that leaves the first sub-goal. Second sub-goal. Should be gone, yeah. We need to state that A is less than or equal to B. Yeah, okay. That does that. Okay, and now we are basically done with this. Okay, so yeah. Okay, so that's the second lemma, which is the last task for exercise number 2. That's it. Yeah. So I hope was okay. Yeah. Please, if you have any questions, post them on the Piazza forum. Any suggestions for the tutorials, also post them there. Thanks.